So this is my Quideo. The basic question talks about the most popular car colors for vehicles in North America in 2000. This is the data that was given by the worksheet. I just wanted to rewrite it to make it look a little bigger. So you can see they sorted it by color and then the probability. Part A of the basic question asked, what is the probability that the vehicle you choose has any color other than the 6 listed? So to take that, you needed to add up all of the probabilities that they gave you and subtract that from 1, and you were left with 0.303 or 30.3%. For part B, it asked, what is the probability that a randomly chosen vehicle is either silver or white? And or is a keyword for the addition principle of stats. So you needed to add the probability of silver cars and white cars. And that was 0.176 and 0.172. And that gave you 0.348 or 34.8%. For the last part of the basic question, it asked, when choosing two vehicles at random, what is the probability that both are silver or both are white? So there's the or again, so it means to add, but when it asks that both are silver when choosing two vehicles, that means you needed to add it because it would be like choosing a silver, and that and means to multiply. So you would multiply each of the probabilities by itself and then add those together, and that's when you get 0.06056 or 6.056%. The advanced question talks about an experiment that was done by some researchers who believe that those who ate more fruits and vegetables that are rich in antioxidants would have less of a chance of getting colon cancer. For part A, they asked what was the explanatory and what was the response variable in this situation. And I said the explanatory variable was the antioxidant and the response was colon cancer because they wanted to see if antioxidants lessened the likelihood of colon cancer and not the other way around. So that would make the antioxidant explanatory and colon cancer response. For part B, they wanted you to outline the design of the experiment and show how to split up the groups. So they had 864 subjects and they wanted to split it into 4 groups because they wanted to test vitamins A, C, and E, and then they needed a control group, so they had a placebo on that 4th group. To make them all even, I think they did 864 divided by 4 because that would make it even at 216 subjects per group. Part C says to assign labels to the 864 subjects and use table B starting at line 118 to choose the first 5 subjects for the beta-carotene group. So for that, you just flip to table B in your textbook and went to line 118, and then you grouped the numbers by 3s. So we would make 700, 600, that sort of stuff. And you found the first numbers within 864 that occurred in line 118, and that was 731, 253, 304, 470, and 296. Part D states that this experiment was double-blind, and it asks what does this mean in the context of this problem. And that means that both of the subjects and those administering the vitamins did not know who got which vitamins. The last part of the advanced question asks about lurking variables that could have changed the data in this experiment. And I said that those who tend to eat a healthier diet than those who tend to eat less healthy most likely lead a more healthy overall lifestyle. So those who eat vegetables probably are the ones exercising, drinking enough water, really treating their bodies well. And that would reduce the likeliness of colon cancer because I looked it up. And according to mayoclinic.org, so it's .org, so you can trust it, a diet in high in red meat and processed meat actually increases the likelihood of developing colon cancer, as well as having a sedentary lifestyle. The final question is the AP question, and it asks about a situation involving treatments from antibiotics that cure common ear infections for children. So, antibiotic A had a 60% chance of curing the ear infection, and that cost $50, but antibiotic B had a 90% chance of curing the ear infection, although it cost $80. So, the two different plans that were proposed in this problem was Plan 1 and Plan 2. Plan 1 wanted to try antibiotic 1, and if that didn't work, they would switch to antibiotic B. And then for Plan 2, they would start with B and then switch to A if that did not work. Part A asks about the probability for each plan. So for Plan 1, you needed to multiply 0.4, which is the probability that antibiotic A would not work, times the probability of 0.9, which is the probability that antibiotic B works, and you get 0.36, and then to that you need to add 0.6 because that's the probability that antibiotic A works in the first place, and that all adds up to 0.96 or 96%. And then for Plan 2, same thing, 0.1 times 0.6, which equals 0.06, plus 0.90, and that also equals 0.96 or 96%. Part B asks about how much each plan would cost. So you needed to multiply the cost of antibiotic A, which is $50, by its probability that it'll work, which is 0.6, and then to that you needed to add the 0.4 probability times 130, because that's how much it would cost having antibiotic A and B, and that would be $82. And then same thing for Plan 2, but you're going to go 0.9 times $80 plus 0.1 times $130, and that gives you $85. The very last part of the AP question asks, based on the results of Part A and B, which plan would you recommend? And explain your recommendation. And I said, since both plans have equal probability of 96% of curing the child, I would choose the plan that costs the least. That plan would be Plan 1 at $82 instead of Plan 2, which is at $85. It's only a $3 difference, but to a family on a budget, or maybe a family who has lots of children with all ear infections, or maybe a double ear infection, those $3 could add up very quickly. So I would go with the least expensive one, which would be Plan 1.